In this lecture, we will go over memory reliability and cache coherence. This is the fifth lecture. In fact, it's the last one on the concept of memory. So we'll begin with the concept of memory reliability. So far, in all the lectures on memory, we have been assuming that memories do not forget, which means that whatever level that we look at in the memory hierarchy, whether it be right at the top with the cache or all the way to the bottom with the hard drive or the server, we have memories that are very reliable and don't forget whatever they store. So whatever bits we store in them, if we try to look at them or read them later on, they will remain the same. But that assumption may not be true all the time. So even if we have a very fast memory, unlimited amounts of very fast memory, which is sort of the main goal here, if it is undependable or unreliable, then it is not going to be very attractive. So by using redundancy, and specifically we'll look at the use of parity bits, so that we have nearly unforgettable memories. So we'll see how we can do two things with redundant bits. So we are going to actually increase the size of the number of bits we want to store, but our goal is to see if we can detect errors in the bit pattern, or better, can we detect as well as correct bit errors. So we'll see how we can use redundancy to detect and correct errors. So parity codes, called Hamming parity codes, are very useful in doing this. A parity code is essentially count the number of ones in a word, and if the number of ones in a word are odd, then we say that that particular word or a set of bits has odd parity. So count number of ones. If it is odd, then it is odd parity, and if it is even, then it is even parity. So for example, if we had a 4-bit sequence or word as, say, 1011, this is in binary, the number of ones in this word are 3, which implies that it is odd parity. So to distinguish between odd parity and even parity, we can use a parity bit. So when a word is written into memory, we not only write the word into the memory, we will also write the parity bit along with it. And that parity bit is computed by counting the number of ones in the word, and if it is odd, the parity bit is 1, and if it is even, the parity bit is 0. So for example, in the previous word, our 4-bit word was 1011, and our parity bit, say small p, because it was odd parity, parity bit is 1. So what we'll write is, we'll not write just the 4-bit word, instead we will write the complete 4 plus 1 bit word. So that is going to be 1011, and we can pad that parity bit way at the end. So by doing this, by storing this 5-bit word instead, you can see that 10111 is going to have even parity. In fact, no matter what word we look at, it is always going to be stored as an even parity word, because this bit will adjust the parity at the end. So parity of n plus 1 bit word, where that one is the parity bit and n in our example is 4, in a general case it's n, should always be even. So we are always going to store in memory, write in memory, the word written is always going to have even parity. So when we read it, and it turns out that it is odd parity, we know that at least one bit is going to be in error. So that's the way we can use parity as a simple measure of at least detecting one bit error. Note that if you have 2-bit errors, they cancel out, and the parity will not be changed. So this can be used to get a sense of errors for odd number of bits. But also note, this is probably a very important note here, the probability of error, the probability of error for one bit error. So probability of one bit being in error, probability of one bit error is going to be much greater than probability of 2-bit errors is going to be greater than probability of 3-bit errors, and so on. So if we have a process to sort of attack the highest chance here, which is the 1-bit error, then we are going to be okay. And just as a safe side, we can probably go to the second level. Even if we cannot correct the errors, can we at least detect 2 errors? But going to 3 or higher for any given bit sequence, the chance is going to be lower and lower as you go for higher number of bits per a given word. So that's a very important aspect that goes into the design of these Hamming codes. All right, so that's a quick discussion. We'll elaborate on a few things as we go forward. So next, let's see how we can use this parity code for error detection. Note that we ideally want to detect as well as correct, but right now we are looking at how do we detect errors. So to do this, we are going to have to define a few key, some terminology here, some key things that we calculate about Hamming codes. So let's start with answering the first question here. What is the Hamming distance of the bit patterns below? So over here we have codes, two binary codes that are 8-bit long, and we are going to find the Hamming distance. Well, Hamming distance is essentially the number of bits that are different. So Hamming distance is defined as number of bits that are different. This is per location. So as you can see here, we have the first 3 bits that are different, and the rest of them are exactly the same. So the Hamming distance over here is going to be 3, because 3 locations are different and the rest 5 of them are the same. So the number of bits that are different is going to be 3. Okay, so going on to the second question here. Show the 9-bit pattern used to store 42. So in decimal the value is 42. The same number 42 in binary is 00101010. That's a 8-bit pattern. We are going to have to make a 9-bit pattern by computing the parity bit, and then we are assuming that words are written to the memory with even parity, and the parity bit is located to the right. So the first thing that we can do very easily is write the 8-bit word, which is 00101010, and then as you can see here, we have 1, 2, 3 ones, so odd parity. So we are going to add one more 1 at the very end, and that's what we are going to store in the memory. So that's the 9-bit pattern that is going to be stored, and again this is going to have even parity, 1, 2, 3, 4, even number of ones, so even parity. So the parity bit 1 is highlighted in red here. Now the next question here is, we have some 9-bit pattern that is given to us. This is being read from the memory. So now we are looking at the other side. Storing is done. Now we are trying to read it and check whether error is there or not. Um, and as you can see here, we are simply going to have to find out the parity of the 9-bit pattern to check whether a single error has occurred or not, or should the system signal an error or not. So let's see, how many ones do we have in this pattern? We have got 1, 2, 3, 4, 5. So we have got 5 ones, which means odd parity, which means that we are going to have an error. So should the system signal an error? Well, yes. The reason being 9-bit pattern has odd parity. 9-bit pattern has odd parity. Notice over here the parity bit is also being included in that calculation. Next, there's another 9-bit sequence over here being read from memory. In this case, how many, what is the parity? So let's see, 1, 2, just 2. So even parity, which means we are good. So no. So I hope that gives you a sort of a brief idea about where we are going with this Hamming code. We are using redundant bits. As you can see, our data was 8-bit, but we are adding one more bit here. We could actually go on and add more number of redundant bits to get the ability to correct errors or detect more than one error. So we'll be doing that in just a bit. But we are using redundant bits to get some error detection going. All right. So the next obvious question is, can we correct those errors that happened? Uh, and the answer is yes. Hamming came up with a Hamming error correction code, in short ECC, which allows us to perform single error correction. So no more than one error correction can be done. So for this, several assumptions have to be made. The first assumption is the Hamming distance. It is a Hamming distance 3 code, which means that the minimum distance between any two codes in the set, minimum distance between any two codes is 3. So we saw earlier how we can find the Hamming distance, which is essentially the number of locations in which the code word is different. So the number of bits that are different. And in this case, we are limiting that to at least 3. So we can have 4 bits that are different between those two codes, or 5 bits or more, but we cannot have 2 or 1. So we are limiting that. And there is a reason for limiting that to 3. The reason is, if we use a code that has a minimum distance of 3, and even if we have a single bit error, that would actually be closer in terms of Hamming distance to the correct pattern than to any other valid pattern, because any other valid pattern will be at a Hamming distance of 3 away, because that's the limitation here that we have set. But so every single bit error will actually be closer to the correct pattern. So it will be easier to detect and actually go ahead and correct it. So that's a constraint that we are applying to this Hamming error code here. For single error correction, if you want more capability than that, then that Hamming distance, we might have to change that limitation. All right, moving to the third item here, the extra parity bits or the redundant bits used to allow the position identification of a single error. So we are not going to have one parity bit, we are going to have more than one parity bit, and all those extra parity bits is going to allow us to identify where that single error occurred. The code word length. So the code word length is different from the word length. So suppose you have 8-bit of data, you could pad it with some parity bits, and then you get a code word. And those limitation of Hamming distance is for the code words. And we can find out the length of a code word, and this is the maximum length, by the way. We can be lesser than this. So these are the number of uh, the codes in a set, where R is the number of redundant bits or the parity bits. If R is the number of parity bits, then the code word length is going to be 2 raised to R minus 1. So for example, if we have R as 4 parity bits, then we can have a code word length of 15 bits, and that's the maximum. We can obviously reduce that to 11 parity bits or 11 code word length or 12 code word length, and we'll see an example with 12-bit pattern. But the maximum that you can get to achieve single error correction is 15 bits if we have R as set to 4 parity bits. So those are our redundant bits. No information, just for correction of single error. Okay, let's move up here. So there are a few steps that we are going to go over that will help us identify the location that has an error, if any, and if we know that that bit is an error and we know the specific location, we just flip it to correct that error. So what are the steps involved in Hamming error correction code? The first step is start numbering the bits from 1 on the left. So as you see in this table over here, the bit position starts with a 1, which is very different from the traditional bit numbering scheme that we use, starting from 0. So we are starting from 1 here, so that we talk about the first bit, second bit, and so on for the parity and the data, all the bits. So we have bit position going from 1 to 15. So I'm assuming, if I relate this back to our previous slide, if I have 4 parity bits, then I can get a code word length of 15, and that's what I have over here. I can stop at 10, I can stop at 11, 12, but I get a maximum of 15 as the code word length. So those are my positions: bit position 1, 2, 3, and so on, all the way to 15. So I'm going to write that, and then the second step is mark all bit positions that are powers of 2 as parity bits. So as you can see here, the parity 1 is, let's see, 1 is 2 raised to 0, 2 is 2 raised to 1, then I have 4, which is 2 raised to 2, 8, it is 2 raised to 3. So all the powers of 2, I don't need to go more than 8 because I don't have bit position 16 here. All the positions which are powers of 2 have been used for parity. So where are the parity bits? The parity bits are at 1, 2, 4, and 8, written as P1, P2, P4, and P8. So those are parity or redundant bits. Where are the data bits going? Well, all the other bit positions are used for data. So 3 is data 1, 5 is data 2, 6 is data 3, and so on. D11 is on the last location here, which is 15. So this can give me a maximum of 11 data bits and 4 parity bits to be able to correct one error. Okay, so that's about the bit position and the encoded bit, which bit goes in what position. So we have talked about that. Let's move on to the next slide here. We continue the discussion of steps to calculate the Hamming code, error correction code. Now, the position of parity bit determines the sequence of data bits that it checks. So for example, if I zoom in over here, bit 1, now how do I find what goes, what bit, should I write a 0 here or should I write a 1 here? Well, for that I would need to check bits that are in location 1, 3, 5, 7, 9, and so on. So let me highlight those positions in blue. So I've got 1, 3, 5, 7, 9, 11, 13, and 15. Well, what is so nice about those particular bits? Well, what is unique to only those bits, those are the odd number of bits, is that the rightmost bit is 1 for those bit positions. So 1 is 1, 3 is 1 1, 5 is 1 0 1, 7 is 1 1 1, and if you go down that list, the rightmost bit is 1 for all those locations. So I'm going to use the parity bit coverage for 1, 3. I'm going to use P1 for 1, 3, 5, 7, and so on. Similarly, I'm going to use the parity bit 2 to cover 2, 3, 6, 7, and so on, which is detailed over here in this list. Bit 2, which is 0, 0, 1, 0, that stands for 2, checks the bits 2, 3, 6, 7, 1, 0, and so, 10, 11, and so on. And as you might imagine, this is the rightmost bit was 1 over there. Over here, the second to rightmost bit is 1. And similarly for bit 4, the third to last bit will be 1 for locations 4, 5, 6, 7, and locations 12, 13, 14, 15. And for P8, parity bit 8, those will be positions 8 all the way to 15. So that's how we are covering those locations. And as you can see, each bit is covered by 2 or more parity bits. So for example, if I look at D3, D3 is being covered by 2 parity bits. Those are P2 and P4. And say D9, D9 is actually being covered by P1, P4, and P8. So as you can see, we have at least 2 bits, 2 parity bits covering each bit, each data bit. We are going to compute those parity bits P1, P2, P4, and P8 such that we create an even parity for each group. So in one group, so let's highlight the group. In one group, and let's call that group 1. Group 1 will include P1, D1, D2, D4, D5, D7, D9, and D11. The group 2 will include all the ones in that particular row that are marked. Group 4 will include these 4 and those 4. Group 8 will include all those 8. So we have to write P8 such that that particular group will have an even parity. We have to write P4 such that that particular group will have an even parity, and so on. I hope you get the idea over there. Okay, so let's move ahead and see how do we know if there is an error. So if we do all of that, how do we actually go through this process and find out if there is an error or not? Well, we know what the code word is going to be. If I go back over here, I know those 15 bits, that is going to be my code word. That is what I am going to write to memory, and whatever I write to memory is going to include two things. Data is going to be, what do I have here, 11 bits of data if I'm using all 15 locations, and for parity I have 4. That's what I'm writing. But due to an error in memory, some bits may may change, and I'm going to assume that only one bit error occurs. Let's see how I can find out where it is so that I can correct it. So whatever we read from the code that we read from memory, we are going to check the parity of each group. So for example, we are going to look at group 1, 2, 4, and 8. Then we are going to check the parity of each group, and if we check those parities to be even, meaning 0, 0, 0, 0, then that means that there is no error. However, if we write the parity of group 8, 4, 2, and 1, and we get that to be 1010, that means that there was an error at location 10. And at location 10, as you can see, we have bit D6 at location 10. So if we know that that particular bit is in error, all we need to do is flip that bit from 0 to a 1 or 1 to a 0, and we have corrected that code. So correct the error by simply inverting the value of bit 10. So that's how this process is going to work to allow us to detect one error and correct one error. So SEC, single error correction. Um, let's see an example about this, which hopefully we can work through this to give a little bit more insight into all of that. Um, so let's suppose we have a 1 byte data, so 8 bits of data that I want to store or write to memory. Those 8 bits of data are given to me, and I have a 12-bit Hamming code that I want to generate for error correction using those 8 data bits. So in this case, I'm not using the total 15-bit code, I'm only using 12-bit code. So let's see if I can generate that code on this slide over here. So the first thing that we do is leave spaces for parity bits, because we know that parity bits occupy position 1, 2, 4, and 8. So I'm going to have to leave the spaces for those. Leave parity bits, and the 12-bit pattern is going to be, say I have 1, 2, parity bits are unknown, then I have 1 from the data, then I have 4 is blank, then I have 2 zeros from data, actually I have 2 zeros and a 1 from data, P8 is blank, then I have the last 4, 1, 0, 1, 0. Alright, so those are going to be my, so I need to fill out the 4 uh, locations. So I've got P1 here, P2 here, P4 here, and P8 here. I need to find those out so that I can fill those bits. So let's see how I can do that with P1. So first, P1, position 1. What does it check? Position 1, I know that it checks, if I go back all the way, I know that position 1 checks 1, 3, 5, 7, 9, and 11, and so on. So I'm going to check those odd bits over here. So coming back here, position 1 checks bits 1, 3, 5, 7, 9, 11, and so on. And if I highlight them, so for this guy it's going to be this, let's see, that's 0, and alternate, and alternate, and alternate. Okay, so if I count the number of ones here, I've got 1, 2, 3, 4, which means even parity. So 4 ones, even parity. Even parity means P1 should be set to 0. So I've got that over here. So what I'll do is I'll simply erase this and write my answer that I computed to be 0. Next, if I do the same process for the remaining ones, I will be completing this. So if I do that, copy and actually paste it quickly, let's see, done. I need to change that to 2. These are going to be different, that's going to be different, that is going to be different, that is going to be different. So let's see, position 2 checks for bits 2, 3, 6, 7, 10, 11, and so on. So let me highlight that with a different color. Maybe I choose pink for this. I've got 1. See, that is going to be checked. The next one is unknown. That is going to be checked. That is going to be checked. That is going to be checked. And that is going to be checked. Alright, so if I check all those, I have 1, 2, 3, 3 ones in that. So P2 is going to be a 1 to make it even. So I can write my P2 here to be a 1. Next, I'm going to do that same thing again, but for position 4. The bits are going to be different, the number of ones are going to be different, and that is going to be different. Let's see, position 4 checks the bits 4, 5, 6, 7, then 12, and then 4 bits there, and so on. So let me erase the highlights and re-evaluate where I'm looking at it. So for the next one, I'll pick yellow for position 4. I'm going to start here. That's 4, 5, 6, and that's all I have, and then I have 12. So let's see. This is going to be just 1, 1. Which means I need P4 to be a 1 to make it even parity. So erase P4 location and fill up with 1. Last is going to be P8 here. So erase, check bits and number of ones and that and that. Okay, and this is going to be 8. It's going to check for bits 8, 9, 10, 11, 12, and so on. We don't have others in this particular one, but we are just writing them. So let's erase the yellow highlights which were for the previous check and highlight the last one, say from the 8, 9, 10, 11, so from the back. So for the fact 4, 12, 11, 10, 9, and 8 is unknown. So I've got 2 ones there, which means P8 is going to evaluate to a 0. So I'm going to go there, erase P8, make it into a 0, and done. And just for clarity, I will erase the highlights because I don't need them anymore, and done. I've got a 12-bit pattern that we generated for Hamming ECC. So 0, 1, 1, 1, 0, 0, 1, 0, 1, 0, 1, 0. So that's 12 bits with 8 bits corresponding to the data, 4 bits corresponding to the parity bits. Okay, so let's, once we have generated those codes, now let's do the other way. Let's see, the final code word written on this slide is the same as the one that we derived in the previous example. Now we are assuming that the memory had some sort of a problem and we accidentally had a bit error on bit 10. So that particular bit 10, because we have 12 positions here, that's 12, 11, 10. That bit 10 has changed. Earlier it was a 0. Now it flipped to a 1. So I'm showing the error in red. So if that is the case, let us see if we can actually go through this Hamming ECC steps to actually find and correct that particular error. So for this, let's start with group 1. So group 1 has 1, 3, 5, 7 bits. So I've got position let me write down the code word first and then I can highlight them. So 0 1 1 1, 2 zeros 1 0 3 0 3 ones. That's the code word that I read, and the positions that are going to reflect group 1 are going to be 1 3 alternate 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 alternate. So if I count the number of ones here, I've got 1 2 3 4 number of ones. Even parity. So that's good. We wanted to make sure that each parity group has even parity when we store it. So when we retrieve it or read it from memory, if it has even parity, that means that error did not occur in those bit locations. We go through this same process for group 2. Alright, let's see. Group 2 is going to be over here. And I'm simply going to erase that. Erase the number of ones. I don't know the parity. I don't know whether it is okay or not. This is also going to change. So group 2, the locations are going to be 2 3 6 7 and so on. So I will highlight that as let's see, there 2 3, then 6 7, and then last 2 there, 10 11. In this case I've got 1 2 3 4 5 ones, which means I have odd parity. That means I have an error in group 2. Next I check for group 4. So let's see if I can do this. Perhaps I can fit group 4 over here, and then I will selectively erase something. Number of ones I don't know. So this is group 4. So for group 4, the locations are going to be 4 5 6 7. So that's going to be starting from here, 4 5 6 7, and then I also have 12. This is going to have, what is that, 2 ones. So even parity, that means this is going to be okay. And now that I have seen all of this, I will simply resize this and make it slightly smaller so that we can take a look at our last group, which is group 8. So group 8, erase number of ones, parity, okay, I don't know. Okay, let's see, group 8, highlight the locations. It's going to be coming way from the back here. I have 12, 11, 10, 9, and 8. I sum up all the ones. I have 3 ones there. So odd parity, that means that I have an error again. So as you can see, I've got an error in group 2 and error in group 8. So error in P2, P8. So that means that I've got an error in bit 10, which is pointing to the location that actually had an error. So by just flipping it, I will have corrected it, which means that if I flip just that bit, I've got 0 1 1 1 0 0 1 0 1 0 1 0, which is the 12-bit pattern that I stored. All right, so that's how the error detection and single error detection and correction happens using the Hamming error correction code. Alright, so let's stop, well, let's not stop with single error correction. Let us see if we can actually get single error correction and double error detection. So as we pointed earlier, the probability of one bit being in error is much higher than probability of 2 bits in the same code being in error, and so on. So if we have the ability to correct one error, and if we at least are able to know whether two errors occur or not by detecting it, we will have a better algorithm. So let's see how we do this. We'll not go through all the details, but we'll just point out how it is done. So we add an additional parity bit for the whole word. As you see, as we saw earlier, we had parity bits for each group. Now we have an additional parity bit, and we are calling it p sub n for the entire word. So we have increased that number of parity bits here. We make the Hamming distance 4. So from 3 we have gone to 4. So the minimum Hamming distance between any two code words in our set of code words is going to be 4. So to decode, we are going to assume that H represents the single error correction parity bits. So for example, it is the set of P1, P2, P4 and P8 if we are looking at a similar size of the code. So H represents those single error correction parity bits. So we could have four possibilities over here, meaning I could have the whole word parity being even or odd. So Pn could have an even parity or odd parity, and on top of that I can have the parity of these four group parities be even or odd. So H is even means that these four have even parity. H odd means these four have odd parity, and so on. So we end up with four possibilities over here. H is even, Pn is odd, and so on. So for each of these, if we get H as even, Pn as even, that means that we don't have error. If we have H as odd, Pn as odd, then we have a situation where we are able to correct one's bit error. If we have H as even and Pn as odd, that means we have error in the Pn bit itself. And if is odd, Pn is odd, then means that double error has occurred. So those are four ways we can apply to this situation. Note that ECC stands for error correction code based DRAM, uses this SEC double error detection with 8 bits protecting each set of 64 bits. So 64 bits are going to be your data bits, and 8 bits are going to be your redundant parity bits for 64 bits. So that's used in ECC DRAM technology. All right, so we'll stop here with the memory reliability discussion, and in the next video we'll talk about cache coherence.